Welcome to continuation of our discussions on topology. We are going to prove that the Euclidean plane is actually a manifold. So I will take you through the proof. Now, we are trying to prove that the Euclidean plane R is a manifold. So we are going to use, as usual, direct proof. Okay. And by direct proof, we are going to use the definition of manifold, actually, to see how it plays out on the Euclidean plane R. Now, by definition, manifold is a Hausdorff second countable space which is locally Euclidean homeomorphic to Euclidean plane. Okay, so we are going to take, these are what we call topological properties of a manifold. We want to see whether R satisfies them. For example, is R a Hausdorff? Is it second countable? Is it locally homeomorphic? Euclidean plane. So we'll take them one by one. Number one. So we say firstly, we want to prove we can start with any. Let us start in the way we write them. Hausdorff. What is Hausdorff space? R Hausdorff will imply that for any x1, maybe x2 you pick in R, there exists some u and v with x1 in u, x2 in v, and u intersection v is empty. Now, can R satisfy this property? Of course, if we endow R with a topology, let's say we have R endowed with a metric topology, a distance function. So the distance between x, y, okay, is going to be x minus y, maybe over t, something like this. Okay. So if you have two distinct points, x, y, the distance function is their distance, the distance between them, and this is a metric. This is a metric or distant topology. Okay, topology. And of course, if you do that, you will find out that the x2 have a line. For example, if you have x1 here, you can have a ball here. Let me say less than, strictly less than. So that I can have an open ball because I'm interested in open balls. X2 here, I will also have, sorry, an open ball around X2, okay. Whatever the distance is, for example, the two will not, so this can be U, this will be B, and we can see U intersection B will be empty. For whatever the values of X and Y, this distance function will not allow them to actually touch each other. For example, if it is 2, what happens? 2 over 3. So we have a, supposing I have 0 here, 1, 2, 3, 4. Suppose this is my R, and I want to pick x1 here, and maybe this is x. Now the distance between the 3 minus 1, the distance is 2. But 2 over 3 now will be something very closely. So I form a ball around with radius 2 over 3. I also form another ball around 3 with radius over 3. You will find out they will never meet. So that means R is Hausdorff. So this implies your R is Hausdorff. Now we go to second countability. What is second countability? By definition, second countable spaces mean that there exists maybe some beta, some base, okay, of course, contained in R, such that for any U, an open set in R, U can be written as union of Bi, okay, collection of Bi where each Bi is in beta. This is the definition of second countability. Now, if you, of course, R, supposing you now form a ball Bi of X, okay, Bi of X, where you require now X to be in Q, the set of rational numbers. This is going to generate some basis. This generates some basis, okay, in Q. So Q now is your basis, okay, and you know that Q is countable. Of course, by definition, we know that Q, the set of rational, is countable. So we have a basis which is second, is countable. It's second because it's also second countable because now if you now take the union of all the Bi of X, where X is in Q, it is going to generate the whole of R. So that means this is second countable space. So we are done with second countability. I think what is only left is to show that there is a homeomorphism between R and R. So that means there exists phi from R to R such that phi is a homeomorphism. And I think without loss of generality, all of us know that this is straightforward because the mapping, if we can ever use identity map, and it will map every open ball U. So phi will take a U, of course, in R, to another U, to the same U, of course, in R. And because the domain arranged at all R, this map is also going to be continuous, and the inverse is also going to be continuous because the phi inverse will also take the same U back to U, and they are all in R. So this is actually a homomorphism. So that means R is a manifold. Because it satisfies all the requirements of manifold. It is Hausdorff, it is second countable, it is locally Euclidean to R itself. So you are welcome to next presentation.